This is part 3, the equation of state from modeling the universe. So we're starting off here with the ideal gas law, PV is equal to nRT. And then we're going to imagine a single photon traveling in the x direction with the momentum capital P. Now, you have to keep this in mind. Before, on the previous page, we already used a little p for pressure. So because we already used little p, now capital P we're using for the momentum. But ordinarily we use little p for the momentum. Okay, so remember from Physics 161 that the change in momentum is equal to the integral of the force with respect to time. So this is the impulse momentum relationship. If the force is constant, then this equation just becomes change in momentum is equal to constant force times change in time. Now, you're starting off with a photon going this way. If it hits the wall and then rebounds and goes in the opposite direction with the same momentum, then the magnitude of the change in momentum is equal to twice the initial momentum. Okay, so that gets us equation 6. And then for equation 7, we're looking at the total number, capital N, of photons in the box, and then relating that to the product of the number density of the photons and the volume of the box. Our box has a width of CT, and so any photon located within a box of this width and traveling in the x direction at a speed c is going to hit the wall during this interval. Okay, so again, you're going to read through this on your own. The width of our box is c times t. The number density little n is equal to the number of photons divided by the volume. This area here is a, so the volume of my box is this distance d times a, and this distance is c times t. So that gets us equation 7. On the next page, we're going to assume that for all the photons that we have in our box, a third of them are moving in the x direction, the other 2/3 are moving in the y direction and the z direction, and of the third of the photons that are moving in the x direction, half of them are moving in the positive x direction, and the other half are moving in the negative x direction. So we get this equation here, which is coming from equation 6 and equation 7, and then we have 1/3 for the photons traveling in the x direction and a half for those going in the positive x direction. Okay, and that simplifies to the equation that we have here. Pressure is equal to force over area. These two equations give us this equation here. The energy of the photon is equal to the momentum times c. This is true, remember, because the speed of the photon is c, and it has no mass, so the energy is equal to the momentum. So these two equations together give us equation 8. This equation is something that we've seen many times before. I think it just looks a little funny here because we're writing it with a capital P, but remember, for the photon, the energy is equal to PC. Okay, and then the energy density is the product of the number density and the photon energy. And then we get the equation of state for the photons. I thought it was helpful to write out what everything is since we have 2 different P's in a row, which looks kind of like a little P. So this is the pressure of the photon. This is the energy density for the photon. So this is the equation of state for the photons. Now we're going to look at the equation of state for matter. And the derivation is exactly the same, except that the box that we have here, this was the speed times t. So for matter, the speed would be v instead of c. And so if we make that change, this is just like equation 8. Here we have the pressure is equal to 1/3 times n times the momentum that was pc here, which became e. Now it's just p times v. And PV is equal to twice the classical kinetic energy. So remember, the momentum is equal to m times v. Kinetic energy is equal to 1/2 mv squared. If I take one of those v's, I can say m times v is equal to p, and then I'm left with another v and a 1/2. So if you bring the 2 over to the other side, p times v is equal to 2 times the kinetic energy. And if you read what we have here, the pressure of matter is effectively 0, and so that gives us our equation of state for matter. Okay, that concludes part 3. You can finish reading through part 3 on your own, and then we'll move on to part 4.